The Collaborative Research Center Offshore Megastructures is performing basic research for the large offshore wind turbines of the future. A rated power of more than 20 megawatt per turbine and a rotor diameter of more than 300 meters is what we are looking at. My name is Raimund Rolfes and I'm the speaker of this largest German basic research initiative on wind energy. The core idea of the center is to develop a digital twin of the turbine that is continuously adapted to the real turbine and thus provides always actual information on the status of the turbine. By this digital twin, we will integrate design and installation with operation and decommissioning of the turbines. At the end, by this means, we will improve the designs and enable more economic operation of wind turbines and farms of the future. More specifically, we are looking at wind and wave loads. We are looking at new design principles for the rotor and the substructure, and we are looking at monitoring and control of the turbines. And finally, all new methods and tools will be integrated into our digital twin.
Offshore wind turbines with increasing rotor diameters will also show increasing dimensions in their substructures, affecting the development of wave and current-induced loads on the structure. The details of the flow field around more complex offshore structures are still largely undocumented and can be affected by a variety of factors like the geometry and the orientation of the structure or the properties of the incident wave and currents. To address this research gap, we conduct physical model tests in a variety of different facilities. For example, in this small-scale wave current flume, where we measure wave and current characteristics close to different structures, as well as loads on the structure itself. To assess the scale effects introduced by this small scale and allow for more detailed measurements of pressures along the structure, we combine these measurements with tests in large-scale wave current flume, 10 times the size of this one. In this way, we are able to identify if there are any relevant thresholds in the loading on size-increasing offshore substructures, which need to be kept in mind in the design process of the offshore wind turbine of the future.
Offshore structures experience cyclic loading, which, in a simplified way, affects the structural integrity through induced damage in the form of accumulation. The lack of a validated design method to address this effect makes a simple, transparent prediction approach for the cyclic foundation behavior necessary. To achieve this, we investigate cyclic soil response through specialized laboratory tests like cyclic direct simple shear, quantifying damage for various scenarios. To gain knowledge about the system response itself, we conduct small-scale tests using many sensors to study stress redistributions and three-dimensional dissipation effects. However, this isn't suitable for a design. Therefore, we combine laboratory knowledge with finite element analysis. We look at the response of one element and transfer this with a developed procedure to the overall cyclic system response. We validate our new design approach with observed behavior from model tests and are able to quantify the cyclic risk.
The offshore megastructures studied in the Collaborative Research Center 1463 are based on advanced technology and are impressive in their size and complexity. However, ensuring their safety and longevity requires regular monitoring. The CRC has established the cluster control and monitoring as an interface for the operation of forthcoming facilities. The cluster is devoted to coordinating measurement data from its acquisition, processing to its evaluation. The Leibniz University's monitoring test structure in WUNTE is a practical example of putting theory into practice. The tower has numerous sensors densely packed to record the structural dynamics. Additionally, the Institute of Methodology and Climatology also provides data on environmental conditions like wind speed, which is crucial in determining the tower's dynamic behavior. The testing facility located in WUNTE enables experiments to be conducted under real-world conditions and allows for the utilization of multiple reversible damage mechanisms. Thus, it proves to be an ideal testing ground for the mutual collaborations of the C sub-project in the CRC.